Okay, so this is going to be the pre-lab video for the gas stoichiometry demonstration. So we did this on our lecture. And so this is a similar experiment. Now what's different about this experiment is instead of using magnesium, we're going to use zinc. And so that zinc is going to be reacted with HCl to produce our zinc chloride and H2 gas. Now this is going to dissolve, so that's going to be aqueous, and this one is in solution, so that's aqueous, and this would be a solid because it's zinc metal. And so when this is going on, we do need to balance that equation. And so to balance that, we should have a 2 in front of that HCl, and that should be all balanced there. So that's good. And so when we were doing this, that piece of zinc was put inside of our eudiometer, and so that zinc was down here at the bottom. It reacted with that hydrochloric acid, and over time, it released hydrogen, which was collected up here at the top. Now, inside of that volume of gas that we collected, remember that it's not just hydrogen. We also have collected in it water, and that pressure is also going to be related to the height of that column, so that distance between those two. So now, going back, what we're going to do is we're going to look at our data that we've collected down here. So they've given us some sample things like the volume, the temperature, the pressure of the room. And so we're going to start to translate those over into the units that we need, because we're going to ideally use PV equals nRT to solve these problems. We're going to treat it like it's an ideal gas, and so we're going to look for the moles that we're looking for, the moles of hydrogen. So for our volume, the first part is we need to take that 81.5 milliliters. We need to convert it over into liters. Now remember that there's 1 liter is 1,000 milliliters. Cross our units, and so we get something like 0.0815 liters. Good. Let's look at our degrees Celsius. So if we want to change that to Kelvin, we have to add in 273.15. That gives us 295.15 Kelvin, which becomes 295.2 Kelvin when we think about our significant figures. Great. Barometric pressure. We have 29.98 inches of mercury. Well, we want to get that into millimeters of mercury. Now we know that 1 inch is 2.54 centimeters, and 10 millimeters is equal to 1 centimeter. So we can take our sorry about that. We can take our 29.98 inches. We can multiply that by 2.54 centimeters is 1 inch, and 10 millimeters is 1 centimeter, and we're going to get all that in millimeters of mercury. So we find out that there's 761.492 millimeters of mercury. And if we think about the significant figures, we should have 4. So 761.5 millimeters of mercury. And so now we're going to try to figure out, well, we have some other pieces that we need to answer. We need to know the difference in liquid levels between the eudiometer and the beaker. And so that's this difference that they're talking about. So we're looking for those height differences between our acid column and the other one. So the difference in those levels, you can see that this is the height of the solution in the eudiometer from the bench top. So that's a tall one. This one here is going to be in the beaker. And so that difference is what we're looking for. So 19.2, minus 10.0. So that gives us 9.2 centimeters is that height difference. Now it's asking us for the pressure of our water vapor. So we can look for the pressure of the water vapor by going up into here. So this is our vapor pressure table. And so this would be something that always would have to be given to you. It's not something that you have to memorize. And so looking at here, we know that our temperature is around 22 degrees. And so our vapor pressure is about 19.8, and that's 19.8 millimeters of mercury. This is asking us for the pressure caused by the acid column. So that acid column is related to that height. The taller it was, the more that there was. So that difference, 9.2 centimeters. And then it has a conversion factor of 0.772 millimeters of mercury for every 1 centimeter difference. And that's kind of like the pressure required to hold that water up. So it's dealing a little bit with that gravity pulling down on it. And so it only works if there's a difference in that pressure. Kind of like a straw with some suction on it. There has to be a difference in pressure for that water to flow up and break that gravity hold. So this becomes 7.1 millimeters of mercury. And so we want to find the pressure of the hydrogen alone. So the pressure of our hydrogen is equal to our barometric pressure, which is our total pressure, plus the pressure of all the water vapor, plus the pressure of our acid column. So what we want to do is we want to go ahead and take this total barometric pressure in millimeters of mercury, and we want to reuse that to find our pressure of our hydrogen alone. So we're really finding the pressure of the hydrogen as being our P total minus the pressure of our water vapor minus the pressure of our acid column. So our total pressure was this 761.5. Our water vapor is 19.8. Our acid column was 7.1. And so that gives us a total of 761.5 minus 19.8 minus 7.1, 734.6. We need to turn that into ATM, so we divide that by 760, which gives us 0.96657. I'm going to go ahead and write this over here. Eight, really? We have 4 sig figs, so 1, 2, 3, 4. So we're looking at that 5. Now that 8 is higher than 5, so we got to round it up. So 0.9666 ATM. So that's our pressure. And so if we want to find our moles, we can use PV equals nRT. N is equal to PV over RT. We have the pressure of our hydrogen as 0.9666 ATM. We have the volume at 0.0815 liters, and that's the volume that we collected up there. We have our R, 0.08206 liters atmosphere, K mole. And we have our temperature, 292.2 Kelvin. So 0.9666 times 0.0815 divided by 0.08206 divided by 292.2. Just double checking. Oh, that wasn't 292.2. That was 295.2. We get a total of 0.0032520 moles. Think about significant figures. Well, we have 4 from our pressure, 3 from our volume, 4 from our temperature. So our answer should be 3. Now that 2 is lower than the 5, so we can go ahead and get rid of that. And so that's how many moles of our hydrogen we have. Now, looking at our equation, we can figure out, well, 1 mole of zinc is equal to 2 moles of HCl. 1 mole of zinc is equal to 1 mole of hydrogen. So if we have this many moles of hydrogen, we should also have that many moles of our zinc. And so for us to convert that into grams, we need to use our molar mass. Nope, not mole grams. That should be moles. And so our molar mass for zinc is 65.39 grams is 1 mole of zinc. And so this is going to be 0.2127 grams of zinc. And when we look at our significant figures, 7 is greater than 5. And so that should become 0.213 grams. Now, if the mass of our zinc was 0.21 grams, what is our percent error? Well, we can take our 0.213 minus 0.21, divide all of that by 0.21 times 100%, and we can see what we get. So 0.213 minus 0.21, divide by 0.21, and so we get something like 1.43%. But interestingly enough, if we were to pay attention to our significant figures, 0.213 minus 0.21, this really becomes 0.003, which is 0.00 when we pay attention to our significant figures. 0.00 divided by 0.21 becomes 0%. And so we don't really have any error there, but we would take either one. It just means that our mass, we probably should have used a better balance when we were measuring, so that way we could get all 3 significant figures. So that was a sample one with our zinc. For the demonstration that I showed you, instead of using zinc, you guys are using magnesium. Now, magnesium reacts with the HCl in a very similar way. It's still making magnesium chloride, which would dissolve, and it's still going to make hydrogen gas. We still need 2 of those HCl's for each one, and so it's still a 1-to-1. Now, you don't have to worry about the unknown number. That part is fine. But you want to go ahead and work your way through this. And then when you get to the end, you can calculate what your mass of your magnesium is. Once you get all of the way through that, then you can see how close you were, or how close our experiment was, based on our grams that we had, that I had put in there. So do that math first. I don't want your the value of your mass to influence what numbers you guys put out. And then I'll go ahead and I'll tell you the mass when we do the follow-up where I work through this problem as well. Good luck.